Hello there. I hope you are all in a good shape and condition and a good health. I'm ready to continue this chapter chemical kinetics. Let's start today to review a few pictures on the blackboard, just to remind you what you can find here and to get your materials. This is the homepage for 2020 Spring Term General Chemistry 2. So my recommendation, visit this place often. I know when you are logging in into the Blackboard. I'm surprised only one student last time logged was mid-June. So that means this student, I don't want to say names, is falling behind on reviewing materials. So one of the first things you need to check always announcement, and you will see here all the announcements. I'm posting usually the newest announcement. They come first here. That's the first you see. The newest announcements goes on top. This one was on July 4th. Was about the discussions. I created this forum for you to come and discuss how to solve problems. And I'm monitoring this, so I'm hoping you all participate. As a matter of fact, I'm expecting everybody listed here as participating people. The second part you need to check is this one, course content. And here all contents, all lectures will be here. And labs too. The newest material goes on the bottom. So you need to scroll down, all the way down, scroll down to see what is new. And I'm creating new learning modules per unit. So the latest one here is chemical kinetics. So you come here and check what videos. Once you watch one video, you should come and visit several times to see if I have added new videos. You come here and can watch the lecture videos. You can increase the screen, and then okay. That was the recording that is there. So again, just come here and check and the newest recordings. The next part of the Blackboard that you need to come, I recommend you to come and is this one. Visit this one. This is discussion forum. So I'm actually, I think I already have one material there. So yes, this one, chemical equilibrium. So I'm expecting you to come and give your inputs on how to solve this problem, how to improve, in this case, the production of ammonia using the Haber's process. So if you do a good proposal on how to increase the production of ammonia in this industry, you may get the job. Take a look. All right. So that is discussion. And then extra stuff I keep posting is here, course documents. Course documents, you will see all materials like Word documents, PDFs, tables, PowerPoint presentations, they will be here. So I'm seeing here the blue, that means the blue are enabled for you to see and use and download and print it out. So all materials here. All right, the next one is here, assignments. On the assignments section, so you will have some homeworks for you to practice. This is not available, so I'm going to make it available for you because we already are on this one. Like the homework for the first our first chapter, I'm going to make it available right now in front of you, so you can compare the answers, your answers with the answers I'm going to post here. So it's going to make available up to up to August 15th. So you will have enough time during the whole semester to review the material. When I click here, submit, and now you should be able to see the document you can download. Now you can download it and print it out, and that's the answer key for the previous homework. All right, and that's it. It's a brief review of what you can do on the Blackboard, how to get involved into the course. Here, this was the previous one. This is the one that was giving me a lot of trouble. The videos I posted here didn't work pretty well for everybody. So that's why I stopped using this. It should not come here anymore. And all my recordings will be again here in course content right here. So all lecture videos, all lab videos will be here. Everything is going to be here. I'm not posting materials here. This is not going to work. All right, so let's continue with our chapter. Last time we were, I was actually suggesting that you should do some review on logs, basic math, and I suggested some of the things you can do, you can review over there. All right, so the next topic is within this chapter is integrated rate laws. All right, let me approach that as follows. I'll show you one example of how important are graphs of experimental results. When we run an experiment, we collect data, we organize this data on a data table, and then we graph that data table to see the tendency of these numbers, the tendency of the process you are following. And I'm going to use one very simple example that you are familiar with already, which is Boyle's law. Boyle's law is one of the gas ideals laws that you study in Chem 11. So I'm going to use that as an example. I always like to start with simple processes, simple systems, simple examples, So then I can guide you through a more complex analysis. I'm going to use this example to show how important is the concept of graphing. Look on this graph, we have two variables, pressure of the gas against the volume of the gas. And this experiment is easy to perform, is easy to conduct, and usually is done in using a syringe or using this this device I'm going to show you. Let's use this one. All right, this is playing with me, but I have a solution for that. Let's work right here on top of the graph. We can use a device like this, and you will tell me the name of this device. This apparatus here, and we can call this like a machine. Do you remember the name of this? Oops, sorry about that. We have an axle here. Yes, that's the piston. So you put a gas here inside, you change the pressure and find the volumes. So a different pressure, you use pressure 1, put 1 mass. Then to increase the pressure, pressure 2, add another mass. Then pressure 3 and another mass. So every time you add a mass, the volume decreases. Yeah. So initially you have low pressure, that's the first mass. Look at the volume. So you have pressure 1, volume 1. I'm running this at temperature 2. So this is the graph for this experiment. Then increase the pressure. Let's say you double the pressure, pressure 2, and what happened with the volume? The volume goes down. Oh, it's not straight line, but it's supposed to be straight line here. It's too shaky. So it's going to be volume 2. And then increase the pressure, pressure 3, and what happened with the volume? Yeah, the volume will decrease to volume 3. So you can conclude from here that as pressure goes up, then volume goes down. And we call this relationship an inverse relationship. So we say pressure is inversely proportional to the volume. And this symbol here, alpha symbol, is the symbol of proportionality. So it says pressure is inversely proportional to the volume, and then you work this out. But this symbol of proportionality is not helpful to solve problems. It just shows the relationship between pressure and volume. In this case, it's showing that it's inversely proportional. That means if this goes up, this goes down, or vice versa. If this goes up, this will go down. So I like to use this example to demonstrate that graphs can tell a lot of information about the system. All right, again, this relationship here is not very useful to solve problems because you need an equation, and this is not an equation. This is a form to show proportionality. It's a relationship. What do you need in order to have an equation? You need something that has, for example, let me show you an example of equation. You say A equals 2B plus 4, also plus. That's an equation, and you can use this to solve problems. This is something I throw there. But the point is, when you see the equal sign, that's a formula, that's an equation that you can use to solve problems. Another example of equation, perhaps you can identify this one. Y equals mx plus b. Do you recognize this equation? What equation is this? Stop the video and figure it out. Find. What equation is this? What this equation is representing? All right. So since this relationship here is not good to solve problems, we need to work this. We can work this out, this graph, so we can convert this into a equation. In science, we use one mathematical trick, and that is called the normalization of the curve. So we can normalize that. Or maybe you are familiar with the term linear fit. So we can convert or transform, not convert, transform the curve into something, into a shape that we can associate with a formula, with a equation, without altering, without changing the tendency or the numbers of your experiment, because you don't want to change the results of your experiment. You have the numbers, your data table, you can manipulate these numbers to show a tendency in a nice manner. In a way that you can analyze and you can use. And what is the nice manner you want? Usually, all we want is to have something like this. Look, what is that? Straight line. You see, this experiment was run at 3 different temperatures, have the same tendency. As pressure goes up, volume goes down. Pressure goes up, volume goes down. At 3 different temperatures here, and here says that temperature 1 is the lowest one, lower than T2, and T2 is lower than T3. So this is the graph running at a higher temperature for either gas at that temperature. How we converted these 3 curves with this tendency into a straight line? Well, that's the trick. So in order to normalize this, you play. Look what changes were made in the graph. What do you notice? What is different on this graph here compared to this? both graphs represent exactly the same system. And both graphs are using exactly the same data obtained for the experiment. We are not changing the data. Perhaps we have done few modifications, a manipulation of the numbers, but still have the same numbers obtained during the experiment. So what was the change made? This is a graph of pressure volume, and you get the curve with that shape. Whereas on the second one, you have pressure against 1 over volume. And this axis here, this axis here, this is the origin. So this is the x-axis. So on the x-axis, what we have 1 over volume. So on the x-axis, we have 1 over volume. And over here, you see we have pressure. This is the y-axis, and this is the x-axis. So for any ideal gas, when you graph the pressure of the gas against 1 over volume, you always get a straight line. If you graph only pressure against volume, then you get this shape. This is the classical shape of Boyle's law for an ideal gas. And since this is not very useful, because it shows only relationship, it is useful because it shows the relationship, but I mean, it's not useful to solve equations. This is going to be more useful, this relationship, because it shows a linear tendency. And that was the purpose of making this change, to convert that curve shape into a straight line. Why do you want to convert into a straight line? Something that is not linear, you want to convert into linear. So you have your numbers here organized, and you can see the linearity of your numbers. But the linearity is between pressure and 1 over volume. That's the linearity of the on the tendency. So basically, we want to see straight lines. Why? Because we know a very nice formula that represents that tendency, and that is called the straight line equation. Y equals mx plus b. So this is the answer to the previous question. Straight line. This is the equation for the straight line. And that's what we want, because now we can express the relationship between pressure and volume as a linear function like this, with this linear behavior. So who's y here in table? In table, y is p. This is y. So you do that. You say y is p. What is m? Let's work with a temperature 1, the lowest temperature. is the slope of the curve. So it's going to be the slope m times x. What is x? Is 1 over b. And since this is a straight line passing through the origin, then the origin is 0. So that's b. B is the y-intercept. And that happens to be 0 because all this, when we extrapolate this line, it meets on 0. So it's going to be plus 0. I just realized. Thank you for letting me know. Talking about this B, volume. And happens that m, that slope, is constant for the line. So pressure equals the constant, which is the proportionality constant, times 1 over v. You can write this also. You can say P times P equals K. And what is this? Boyle's law. All right, but the point is not to demonstrate Boyle's law. I'm just using that as an example to show how important are graphs. And we can manipulate numbers the variables in order to find the linear behavior of your numbers. Like this manipulation we did here. Since pressure against volume was given a curve, then you play with this. So probably you want to do, because you don't know initially, that's a new experiment, you don't know where, how to get the linear tendency. So probably you want to do 1 over P. If you do 1 over P against volume, probably you get something crazy there, a shape. And that doesn't work. And then you do, okay, 1 over P against 1 over B, and you get something weird. And then you start playing with this. And then you do P over 1 over B, and then you get the nice, beautiful straight lines. So that's it. So the graph of P pressure of the ideal gas against the inverse of the volume will give a straight line, and that will show the tendency, the linear tendency of that relationship there. And from there, you can use the straight line equation and form your formula, your equation. Now, notice that we have the equal sign here. Now we have a formula where you can plug in pressures or volumes. You can calculate from the graph. When you do linear analysis, the computer calculates that for you, or you can do it by hand. And then for initial and final conditions, you will find that PV, P1, B1 equals P2, B2. For initial conditions, final conditions. So you have a nice formula here to work with Boyle's law situations. All right, similar to this, we can do to figure some relationships for to figure out the rate laws. You can even play this. You can take logs. You can take natural logs to get the straight lines. So there are different strategies to make a curve to show a linear tendency, and that's called the normalization of the data or normalization of the curve. So that's what we're going to do to figure the rate laws from graphs. And that is what we are going to call integrated rate laws, because now we are going to graph the rate of the reactions against time. So we are going to introduce the variable time there, and that will help us to make predictions as function of time. 3 different situations we are going to analyze. Using concentration of A, let's remind what we were doing last time. So we have here remember we have a our generic equation A plus B making products. And we know how to write the rate law for that reaction equals rate constant times concentration of A times concentration of B, A elevated to exponent M, B elevated to the exponent N. M and N represents the order of the reaction. M with respect to concentration of A, and N with respect to the concentration of B. M plus N gives the overall order of the reaction. I explained in the previous video the meaning of the order. It has 2 different meanings. 2 different pieces of information can give us regarding the how A and B work together to form products, and that will give us a hint later on to write reaction mechanisms. So far, let's figure how to use these integrated rate laws that will help us to make predictions. Those are actually the ones that will help us to solve some type of problems. So in terms, we're going to describe the new integrated rate laws in terms of concentration of A or in terms of concentration of B. It doesn't matter, because we are going to focus on only one of these reactives, either A or B. It doesn't matter. It's going to be exactly the same concept, because remember, A can be 0 order, 1 order, or 2nd order. Same thing for B. B can be 0 order, 1st order, or 2nd order. So in the first case, concentration of A, again, in a graph of concentration of A against time, is going to be linear for a 0 order reaction. This is key. In other words, you run an experiment of speed of reaction, you measure different speeds of reaction, changing concentrations, and then you graph the concentration of A against time, because you were measuring the concentration of of A at different times in your reaction. So you add A plus B, and then you measure, you know the initial concentration of A, you add B to the reaction chamber, and you have a ways to measure the change of concentration of A. So then you measure concentration of A after 5 seconds, depending on how fast is your reaction. And then you measure again the concentration of A after 10 seconds. Usually you create a very interesting experiment where you have a way to keep track of changes concentrations. Sometimes you do microsystems, you take out this the microsystem A and take the measurement, because once you take it out, you cannot put it back. It's going to change the variables there. So you take measure at 5 seconds, and then at 10 seconds, and then measure after 15 seconds, and so on and so forth. You keep track of changes of concentration of A. So that data, you plug that data in a graph of A against time. And if you get a linear behavior for that graph, then you know it's a zero order. There are the mathematical way I will show you later also. So either way, from the experimental data, you graph it and you get the linear relationship between concentration of A against time, and that is an indication that it's a zero order, and I'll show you how to work it out. And the second situation, when you graph natural log of concentration of A against time for a different reaction, you get linear for first order reaction. And on the third scenario, you graph the inverse of concentration of A, 1 over concentration of A against time for another reaction, and it's going to be linear for a second order reaction. So the linear behavior of different settings of concentration of A will tell you the order of the reaction. I'll show you in a few minutes. So for a zero order reaction, the rate of the reaction is constant, K. So that will be the rate law for the first order reaction. Because remember, if we are working with respect to concentration of A on this rate law, if we say the reaction is zero order, that means concentration times concentration rate equals constant times concentration of A to the power 0. But any number to the power 0 is 1. So K times 1 equals K. So this is the rate law, the shape of the rate law for a first order reaction. For a zero order reaction. For a first order reaction, then the rate law for the first order reaction equals constant times concentration of A to the first power. That's what I did on the previous video. And for the second order reaction, the rate is going to be constant times concentration of A squared, where K happens to be the slope of the line. And notice that for the first case, K has a negative slope. So negative slope, if you can remember, for a graph, y against x, if the line goes that way, we say this is the slope m. For our case, is the constant is positive. If the line goes that way, here, this is for the first case. For the second case, we call this negative slope with that tendency there. So for a zero order and first order, the slope of the line is negative. And for the second order, the slope of the line is positive. So let's see. Let's see the graphs. For a zero order, look, we are going to do three operations of concentration against time. If we plug directly concentration of A in moles per liter against time in seconds, look, we get the straight line. We get the straight line here. And that's it, bingo. We found it at the first try. So this is the graph that is going to describe the first order reaction. And when you see this, when you have a graph of concentration of A against time, and you get a straight line with negative slope, you say that's first order right away. And you can convert this relationship into an equation, because you can use the, again, the equation for the straight line to formulate the equation of this behavior. So what is y? Y is concentration of A equals mx, and what is m? Is negative slope, so negative K times time. Plus the y, the intercept, and the y-intercept happens to be concentration of A at time t. This is concentration of A at time 0, initial, up. So this is concentration of A at any time here, and the B-intercept is the concentration of A at time 0. This is time 0 here. Sorry, I did the opposite. So this is at time t. That means at any time, every of these measurements were conducted at different times. Yeah, this one here, different times. Different times, different values of concentration of A. So we say this is concentration of A at time t, that means any of these times. And when this straight line intercepts the y-axis somewhere here, that will be a time 0. So that will be the initial concentration. Now we have a formula that describes a zero order reaction. Very useful. You can rearrange these terms. Let's keep playing with this to see if there's any other chance to get a straight line. And the second possibility will be, and you can ask yourself, okay, what will happen? What will be the shape of the graph if we plug natural log of A against time instead? On this one, we got straight line and we say, bingo, we got it, that's it. But let's try a different way. Let's try to do natural log of A against time, and look what you get. It's not straight line, so you say, not good. Skip. So that will not show any linear behavior. It's not good. You cannot make an equation from here. A nice equation, of course, you can create a polynomial of this, but let's make it simple with the straight behavior. Now, let's try a different way. Let's try, what about if we try plugging and graphing 1 over A against time to see what we get. And this is what you get. Yeah. Nice curve, right? But that's not what we want. We want to see a straight line where we can manipulate and transform this straight line equation. So yes, this doesn't work. 1 over A against time doesn't work. The only one that works is this. So every time you plug concentration of A against time, that will show a first order reaction. That means you run that reaction, A plus B to form products. That particular reaction, you get the numbers, you plug in, you do three graphs, and the graph that gives you the straight line. For example, that equation for the chemical reaction, when you plug concentration of A against time and get a straight line, you say that reaction is first zero order with respect to A. That's your conclusion from here. The second possibility, another reaction. Let's see another reaction. You have another reaction and you don't know what is the order, right? You run a reaction, it's a pretty new reaction. You created that reaction, you discovered a chemical reaction, and you want to know the kinetics of the reaction. You want to know, for example, what is the order of that reaction with respect to one of your reactives, reactive A. So this is what you need to do. You graph, you collect the data, changing concentrations over the time, and then graph that information. So again, 3 graphs, you need to make 3 graphs to figure the order of the reaction, because again, the concentration of, okay, let me write it here again. A plus B to make product, and we want to know what is the order of the reaction. We want to know what is the rate law. We know the shape. We know the shape. The shape has to be rate constant times concentration of A times concentration of B. We already know this because that is what we call the Rayleigh law. So it has to be this way. But we don't know what is the order of the reaction. We don't know what is M and we don't know what is N because it's a pretty new reaction. And we need to run experiments to figure that out, because that's the only way to figure what is the value of M and what is the value of N. You have to run the reaction, collect data, and then one way to do is graph. And since we have only 3 possibilities, the most common, it could be of 0 order, or first order, or second order. This could be of 0 order, or first order, or second order. Only 3. So you need to do 3 graphs. You can start making graphs at any order, it doesn't matter. First graph you need to make out of this data is concentration of A against time. You need to make another graph, natural log of A against time. So you organize your data, right? You run the experiments. You run your experiments there on your here trials. Experiment number 1, trials, and here concentration of A against time and time. So first experiment, second, and so on and so forth. Oh, this is not a nice graph. Second experiment, third experiment, 4, at least 10 experiments on a serious work. So you know you change the concentrations, you double, triple, like 0.1 molar, 0.2 molar, 0.3 molar, 0.4 molar, 0.5 molar, and you measure the times and the rates as the previous one. Also, you want to calculate the change of concentration over the time once the reaction is working. And then you collect this data and plug this here. Plug it and find what is the shape. And then you add one more column. You need to add one more column here. And that column is natural log of A. Natural log of A is simple. Take your calculator, take concentration of A, find natural log of A, put it here. Second, put it there, and so on and so forth. Every concentration you found, find natural log, and then graph this against time. That's the second graph. And then add one more column to your data. The next column will be what? Will be 1 over A. 1 over concentration of A. So how you do that? Just take, you already have A, concentration of A. 1 over A, take your calculator, 1 divided by concentration of A. Put it here. Second number here, do the same thing. Take 1 over this number, 1 over concentration of A, put it there, and find 1 over A on every measurement. Now you have one more column, and then graph this against time. The time is the same for all experiments. So that's what you have here. And what do you get? And then you observe the shape. If you find a straight line, that's it. That's the order of the reaction. And now, depending on what graph will tell you the order. So look here, concentration of A against time is not straight line. So, not good. This one, natural log of A against time, yes. That is the shape of the first order reaction. All first order reactions forms a straight line when you plug natural log of concentration of A against time. Look here, you're plugging in, you're graphing 1 over A against time, and it's not a straight line, so no. So this graph here will be for zero order if you get straight line. This graph, natural log of A against time, will be for first order, if you get straight line, like in this case. And this is the graph that will help us to find second order. This is for the second order. Second order. So, yes, first order gives a straight line between when you graph natural log of A against time. And then from here we can make a formula. Again, using the straight line equation. So let's work it out. So we have y equals mx plus b. What is y? Y is natural log of A equals m, which is the slope. In this case, we have negative slope, negative k, times x, which is time, lowercase t, plus y intercept, that is natural log of A, concentration of A at time 0. So this is at time t, and this is at time 0. Now we have a nice and beautiful formula for integrated Rayleigh law, first order integrated Rayleigh law. On the previous one, we found a beautiful equation for zero order integrated Rayleigh law, or the integrated Rayleigh law for a zero order reaction. So your reaction will behave in one of your reactives in either way. It's going to be or zero, or first order, or second order. For a second order, what's going to be the pattern? For a second order, you do the same thing. You run, you see the data here, you run concentration of A against time, how concentration of A is changing over the time. You take the measurement, you do one, this is your first table, you make another column, make a second graph, then you create another data table here, another column of 1 over concentration of A, and then you graph that. So here, first, concentration of A against time for a different reaction, and you get no straight line. So it's not zero order. So your conclusion here is this is not You write it there. This reaction that you're running is not zero order with respect to concentration of A. It's not, because it's not linear here. On the second graph, natural log of A against time. What is your conclusion when you see this graph? You say it's not. Your reaction is not. What relationship this will be? It's not first order with respect to concentration of A. And what would you say about here? You will say this reaction is, it is a second order with respect to concentration of A. You found it. Because you got a straight line here in this relationship of 1 over concentration of A against time. So it's the similar, you do this exactly the same analysis on every case. So depending on what you see. Here, what do you say? This reaction you're running is not zero order with respect to A. It's another reaction. You have another reaction. And you graph the data for that particular reaction. And you get this here, this curve. And you graph concentration of A against time. So what is your conclusion? You say that reaction is not zero order with respect to A. What would you say about here, about the order of that reaction? You say this reaction is first order with respect to concentration of A. Because you get a straight line when you plug natural log of A against time. And then, what would you say here? You will say this reaction is not first order with respect to concentration of A. Because you didn't get a straight line when you plug 1 over A against time. And here, exactly the same analysis. You go here and see this shape, straight line, and you say right away, it is. The reaction is zero order with respect to concentration of A. Why? Because you get a straight line when you plug, when you graph concentration of A against time. What would you say here? You will say that reaction, the one that you're working here, that reaction is not first order with respect to concentration of A. Why not? Because it doesn't show a linear behavior when you plug natural log of concentration of A against time. What about here? What do you say about this graph? This graph shows that your reaction is not second order with respect to concentration of A. Why not? Because the graph of 1 over concentration of A, here concentration is missing, 1 over concentration of A against time is not linear. So that's the analysis we can make here. But remember, your reaction has to or 3 or 4 reactives, A plus B in this case, A plus B and C. So you need to do the analysis per every reactive to find the order of every reactive. Right? Similar situation you can do for B. In your reaction, the rate law, this can be 0 and this can be 1. This can be 1 and this can be 0 or 2 or 3. This can be 2, second order, and this can be 0 or 1 or 2. So you can have several possibilities there. So that's how we do analysis of the graphs to find the integrated rate laws. Now let me show you the mathematical way. Let me show you the mathematical way here. Let's see this, let's analyze this actual data. This is the reaction or decomposition of N2O5. This is an actual experiment conducted at 45 degrees Celsius. So they ran the experiment, they took different measurements of different concentration of N2O5 against time. And look what happened. Look at the shape of the graph. What would you say? This is a graph of concentration of N2O5 against time. Conclusion. Write your conclusion. Stop the recording, do the analysis. If you don't know how to do it, go back to what I just said until you know a very concrete answer. And now you can continue watching. And I can tell you this, from the shape of this graph of concentration of N2O5 against time, and based on what I just said on the previous example, my conclusion is that this reaction is not zero order with respect to concentration of N2O5. It's not. So we have an open chance. So if now it's demonstrated that it's not zero order, that means it could be of first order or second order with respect to N2O5. All right. Let's start ruling out the second possibility. We just rule out that it's not zero order. Why? Because it's not given a straight line when you graph concentration of N2O5 against time. Let me go back. You see, you have 3 possibilities. You have to make 3 graphs to find where you get the straight line. If you graph concentration of A against time and you get a straight line, so that's zero order. This graph will confirm whether or not you have zero order. This graph, concentration of A against time, that's what you need to look. Look, what is that? Do I have that? Yes, concentration of A against time, concentration of A against time. That will give you the confirmation of whether or not the reaction is zero order. The second graph of natural log of A against time will give you confirmation of whether or not the reaction is first order. Like in this case, you see, it's not straight line, so you say, okay, it's not first order. The third graph of 1 over concentration of A against time will give you confirmation of whether or not the reaction is what? Second order. Like this one, it's straight line, so you say yes, it is a second order. So you go back here, Straight line, zero order for the first graph. Second graph is first order. And third graph is second order, straight line. You won't find a situation when you get to straight lines. That will be really confusing. And I hope you don't get that. So that will mean that reaction will behave as both zero and first order. I haven't seen that. I haven't heard that. I don't know, maybe it's possible. I haven't heard that. I cannot confirm. You will get, one of them is going to be straight line and the other two are not. So it's either zero order or first order or second order. I read that it's possible to have third order, but it's very complicated. That means the molecularity is 3. In other words, 3 molecules or 3 species participating at the activated complex during the transition state of the reaction. So nature doesn't like that because it increases a lot of entropy in that process. And it's not likely to occur. However, some researchers have found this can happen. It's very weird situation. We have molecularity 3 for third order reactions. All right, let's go back here. We just find that this reaction at that temperature is first order with respect to concentration of N2O. So we can create a nice straight line from there. You see here is down backward. So the relationship there, the relationship is when we integrate, when using derivatives and integrate, we found that natural log of concentration of A at time 0 over concentration of A at time t equals Kt. K, where K is the rate, happens to be the rate constant times time. Now we have a beautiful equation that includes the time variable. And we can use this equation to make predictions, because now we can know the initial concentration of A, let the reaction go, and we can predict what will be the concentration of A after, let's say, 5 seconds. So that will be the concentration of A at time t after 5 seconds. So you can say, oh, I want to know what will be the concentration of A after 2 hours of reaction. And has another application, and we'll see later, like a half-life. Very useful reaction. And you see, if we break this down, we found that has a linear behavior. Look. So it has the shape of the linear straight line equation. This is the one I just did previously. Look. So that was the demonstration, the graphical demonstration for the first order. I did it somewhere here, right? Yeah. Look, it's the same. It's the same. So when we work this out, that's what I asked you to review some properties of logs, because it's important you learn how to manipulate these equations to apply that in the different situations. Let's see. Let me show you here a little bit of that. Make some room here. Okay, for the first order reaction, for a first order reaction, you will have A plus B to form products. So therefore, concentration of natural log of concentration of A against time produces, let's assume this is a straight line. Straight line with negative slope here. M happens to be the negative rate constant. So from here you say, okay, so natural log, okay, let me write this. Y equals mx plus b. That's the straight line equation. So y is natural log of A. This is letter Y. Natural log of concentration of A equals m, and what is m? It's the slope, and happens to be the negative rate constant. The rate constant. It's negative because it has negative slope. Times x, which is time, here, this is the x, time, always use lowercase as a symbol of time, plus b, which is the y-intercept here. So the y-intercept here will be the natural log of concentration of A at time 0. That's the initial concentration. So plus natural log of concentration of A at time 0. Therefore, this is a time t, right? At any time. So you can rearrange this, work this out. And let's say you want to move this around. And you say natural. Now we have this when you have to apply the logs properties. You say the natural log of A at time t minus natural log of concentration of A at time 0 equals negative kt. When you see this, you figure right away what operation is this, right? So how do you represent this operation? That will be natural log of A at time t over natural log of over concentration of A at time 0, which is equals to negative Kt. So that's why I ask you, please go back and review the properties, how to get from here to here. There's a property of logs, very easy property. Please go back and double check how to do this conversion, because you will need that skill to solve your problems. And you will say, hey, hello, but this is not the same as the previous one. What is the difference? You see the difference there? Compare this one to this one. You will see a couple of things different there, but actually it's the same. It's just a different organization of the terms. Look, we have negative here, and there's a way, it's another property to convert this to positive. If I rearrange this the opposite way, I actually can I have room here. You can easily demonstrate that when we change this to positive, we can do that just changing the terms. Natural log of concentration of A at initial conditions over concentration of A at time t equals positive t. So either one. You see here, negative sign here. Negative sign here, but now we have the positive slope. We just do the reverse and we switch terms here, and that is thanks to one of the logs properties. I personally, sometimes you see this in some textbooks, sometimes you see this, it's the same. Just don't forget here you have negative and you need to apply that negative and you do that when you're plugging in your numbers. I personally try to avoid the negative, and I like to use this one. So this is one of the most important equations you are going to use, and this is called the integrated rate law for the first order. For a first order or first order integrated rate law. First order. So we need to recognize that is on the paper with the formulas, it's there. And I'll show you later on how to use this formula to solve problems. Let's go to the second order integrated rate law. And also we are going to learn how to find the half-life. So different ways to express your integrated rate law here. You want to solve, for example, for concentration of A at time t, so you need to take this term out of this portion because this is natural log of concentration of A at time 0 over concentration of A at time t. If you want to get this out, then you can use this relationship here. Basically, what you need to do is to take natural log, anti-log on both sides. So anti-log is another property. You need to remember what is log and what is the anti-log. And versus anti-log. So we have, this is base 10. You have natural log. So also you have anti-log for the natural log. Like in this case, you want to get rid of this natural log here because you want to have only concentrations of this. So it's hard to operate when you have this natural log here. So one way, remember this situation here. This is another mathematical trick. Let's say you have 9. Okay. Let me give you this. A squared equals 25. What is A? So you have a square here, and one way to get the, I'm putting very simplistic example here to show you what is possible if you know the rules. How do you get rid of the square? You want to eliminate the square from your equation. Just take a square root. Square root of the square cancels out, right? Or vice versa. So you say, you rewrite everything again. You say square root of that equals, and if you take a square root here, you must take a square root on the other side too. Square root of 25. So what is the square root of a squared? A. What is the square root of 25? It's 5. You see? Or vice versa. If you have the square root, how you get rid of the square root? Taking a square on both sides of the equation. Similar here. If you have natural log on one side, you want to get rid of that, take anti-log. So you're applying anti-log here on both sides. You say anti-log of natural log of concentration of A over concentration of A at time t equals KT. So if you take anti-log here on this side, you must take anti-log on the other side. Anti-log of this term. So what is the anti-log of natural log of this term? So it cancels out. So this anti-log cancels this natural log, and you get concentration of A at time 0 over concentration of A at time t equals, what is the anti-log of this? So it's going to be E to the Kt. So similar with the base 10. So for log base 10 equals 10 to the x. And for log for natural log, it's going to be e to the x. Now we have this expression, and now we can work with this. If you want to know what is the concentration of A at time t, so you say, okay, concentration of A at time t equals concentration of A at time 0 over E elevated to Kt. Or vice versa. You can find what is the initial concentration if you know the final concentration. So it's very important you practice how to do this. Like this one. All right, the next one. And the next one shows, as I did before, the linear behavior when you plug 1 over concentration against time. In this graph, you see it gives a straight line with positive slope. So your conclusion is this is a second order reaction. For a second order reaction, then the rate law is rate equals reaction rate times concentration of B to the second power. And the second power represents the order, second order reaction. From the graph, we found, I think I didn't do it in the graph for the second order. All right, let's do it here. Can I erase all this? All right. So for the second order reaction, you have A plus B to form products. Then we graph. What is the graph that confirms whether or not you have second order reaction? What you need to do? How do you confirm whether or not you have a reaction with second order with respect to any of those reactors? I've been using A. Let me use B. So you realize that it could be either one. Let's use B. So the graph that confirms if a reaction is second order is the graph of 1 over concentration. In this case, I'm going to use B, concentration of B. against time. And what you should get for a second order reaction, you should get a straight line with positive slope. And that slope happens to be the rate constant, is positive. So we do the same treatment we did for the previous one. Applying that straight line equation plus B. So Y equals 1 over concentration of B equals M, which is K, times T plus B, which is the 1 over concentration of B at time 0, initial concentration, and this is going to be a time T at any time. Now we have the equation for a second order reaction. You can rearrange this around the way you want it, depending on what information, what you want to solve in your problem. Right? Okay. Another application of rate law is half-life. And we'll see the relationship with half-life. What is half-life? This is an example of radioactive decay for iodine-131. Iodine-31 is a radioactive isotope, is a radioisotope. And we can graph the activity of the isotope in a graph of concentration over the time. It's a typical graph of decay. For iodine specifically, iodine-131, look what happened when we graph. What the graph is showing is a behavior. When we graph concentration of iodine initially over the time. So let's say we have the initial concentration is here, and happens for this case that after 8 days the material decays to exactly half of the initial amount. Look, you have initially this amount, and after 8 days the material decays to exactly half. That's the decay. That means the material is transformed into a different material, and the mass is reduced to exactly half after 8 days. What happened after another 8 days? The material also decays through radioactive emission, and exactly after another 8 days, the amount you have here goes exactly half with respect to the previous one. And with respect to the initial, we will be 1/4. What happened after another 8 days? Always 8 days. 8 days is the key. The mass reduces by exactly 1/2 of the previous one. And after another 8 days, the mass goes down again by half. and that is what we call, you can see the half-life of iodine-131 is 8 days. And the way to represent that is saying T 1/2 is 8 days. So this symbol represents the half-life. What is the definition of half-life? And again, this is the symbol for half-life. So you say the half-life is the period of time for a substance undergoing decay to decrease by a half of the initial amount or the previous amount. So that's the definition of half-life. Here is a representation of that half-life. And we can represent this in terms of fraction or in terms of percentage remaining. So after one half-life, look, the material decreases by 1/2. That means initially you have 1. After one half-life, half of that is converted to new material and remains 50% of the initial amount. After another half-life, half-life is constant. After another half-life, look, the amount reduced by another half. Another half-life, another half. And so on and so forth. 1/2, another half. 1/2 of 1/2 is 1/4. Now 1/2 of 1/4 is 1/8. 1/2 of 1/8 is 1/16, and so on and so forth. And the difference is the fraction remaining. And it has been found that radioactive decay follows exactly the same first order kinetics. So copy that. Radioactive decay follows first order kinetics. That means uses exactly the same. You can apply exactly the same first order rate law we just discovered it. So we can apply, remember this is, look, the shape of the first order reaction, first order kinetics with respect to A. Well, it's exactly the same formula we're going to use for half-life of radioactive materials. The radioactive decay doesn't go through zero order. They don't go through second order, only first order kinetics. So it follows this behavior. We can find from here the half-life, because now we can say at time t, we are going to find concentrations for half-life. So let's assume this is going to be our half-life. That means at that time, at time t, we'll have half of the initial. So concentration at time t for half-life is going to be half of the initial amount. That's the definition of half-life. So now we can plug this into the equation. So we have natural log of initial concentration of A over concentration of A at time t, but happens that it's going to be half-life. So it's going to be concentration of A at half-life, which is half of the initial amount. So it's going to be 1/2 of this concentration. 1/2 of the initial concentration here equals K times half-life. Remember, this symbol represents half-life. We simplify this. Concentration of A initial over half of concentration of A initial, that gives you 2. 1 over 1/2 equals 2. Yes or not? 1 over 1/2 equals 2. Not too sure? Well, you can go and ask your little brother or sister. They can help you to demonstrate that. 1 over 1/2 equals 2. So natural log of 2 equals K times half-life. And we can reorganize that and say half-life, this is half-life, equals natural log of 2 over K. Now we have a constant here. What is natural log? You can leave it this way, but you can just find natural log of, go on to the calculator and find what is the natural log of 2. And you will get 0.63. Yeah. So it's going to be constant. So this is going to be the shape of the half-life of any radioactive material. Reactions, you can calculate the half-life of reactions too for first order. So it's going to be like this. Chemical reactions can go through 0 order, first order, or second order. So you can find half-life for 0 order reaction. You can find half-life of a first order reaction, which is this one. Or you can find the half-life of a second order reaction, which is this one. Yeah, look at the shape. And here is the demonstration, similar to what I just did. That is the half-life of second order reaction. However, radioactive material, again, and I insist, goes only through a first order reaction. So in order to solve problems for radioactive materials, we use only this formula and this formula so far. First order. For radioactive decay or dating. It's a very good application of dating. We can date radioactive materials applying these formulas to figure how old, for example, is a rock. So, for example, we can date it using potassium or argon material. For materials containing carbon, we can date the fossil, for example, using carbon 14, which is a radioactive material, very long half-life, and can be used to date it. I'll show you a couple of examples how to do that using these two equations. So that's a big application of dating, and that's why we related this chapter with nuclear chemistry, because we are going to work with that type of nuclear reactions. We're going to play these equations. All right, so I'm going to leave here. The next, and that thing will be the last of the chapter, will be about collision theory, reaction mechanisms, and then we'll solve problems, and that will be the end of the chapter 13. The next is, after that, will be nuclear chemistry, which is going to be shorter than this one. I spend a lot of time, I like to spend, I always spend a good amount of time explaining in detail everything on chapters of equilibrium and kinetics. For the rest of the chapters, now I can go a little bit more faster. And after that, we can plan on the first exam. So our first exam is getting close. Probably next week, by the end of the next week, we are going to post the first exam online. Depending on how far we go, we'll include chemical equilibrium, chemical kinetics, and I hope we can include also nuclear chemistry. We'll see. All right, see you next time.